Hi, welcome to the ComSci 137 lecture. Sunny here. In this module, we will discuss about the data link control. Let's start. The data link control deals with the procedures for communication between two adjacent nodes, or what we may refer to as node-to-node communication or hop-to-hop, no matter whether the link is dedicated or broadcast. Data link control functions include framing and flow control error. Data transmission in the physical layer means moving bits in the form of a signal from the source to the destination. The physical layer provides bit synchronization to ensure that the sender and receiver use the same bit durations and timing. The data link layer, on the other hand, needs to pack bits into frames so that each frame is distinguishable from one another. Framing separates a message from one source to destination or from other messages to other destinations by adding a sender address and a destination address. Destination address tells where the frame is to go. Sender address helps the recipient acknowledge the receipt. A very large frame makes flow and error control very inefficient. A single bit error requires retransmission. Frames can be of fixed or variable size. In fixed size framing, there is no need for defining the boundaries of the frames. The size itself can be used as a delimiter. In variable size framing, which is prevalent in local area networks, we need a way to define the end of one frame and the beginning of the next. Historically, two approaches were used for this purpose: a character-oriented approach and a bit-oriented approach. In character-oriented framing, data to be carried are 8-bit characters from a coding system such as ASCII. Header and trailer are multiples of 8 bits. An 8-bit flag is added at the beginning and end of a frame. Character-oriented framing was popular when only text was exchanged by the data link layers. The flag could be selected to be any character not used for text communication. Now, however, we send other types of information, such as graphs, audio, and video. Any character used for the flag could also be part of the information. If this happens, the receiver, when it encounters this pattern in the middle of the data, thinks it has reached the end of the frame. In byte stuffing or character stuffing, a special byte is added to the data section of the frame when there is a character with the same pattern as the flag. The data section is stuffed with an extra byte. This byte is usually called the escape character and has a predefined bit pattern. Whenever the receiver encounters the escape character, it removes it from the data section and treats the next character as data, not as a delimiting flag. In bit-oriented framing, the data section of a frame is a sequence of bits to be interpreted by the upper layer as text, graphic, audio, video, and so on. However, in addition to headers and possible trailers, we still need a delimiter to separate one frame from the other. Most protocols use a special 8-bit pattern flag as the delimiter to define the beginning and end of the frame. This flag can create the same type of problem we saw in the character-oriented protocols. That is, if the flag pattern appears in the data, we need to somehow inform the receiver that this is not the end of the frame. We do this by stuffing one single bit instead of one byte to prevent the pattern from looking like a flag. The strategy is called bit stuffing. In bit stuffing, if a 0 and 5 consecutive 1 bits are encountered, an extra 0 is added. This extra stuffed bit is eventually removed from the data by the receiver. Note that the extra bit is added after 1 0 followed by 5 1s regardless of the value of the next bit. This guarantees that the flag field sequence does not inadvertently appear in the frame. One of the responsibilities of the data link control sublayer is flow and error control at the data link layer. Please take note that a similar flow and error control takes place at the transport layer. Flow control coordinates the amount of data that can be sent before receiving an acknowledgement. Error control is both error detection and correction. Automatic repeat request, or ARQ, is the retransmission of specified frames anytime an error is detected in an exchange. Additionally, there are 5 protocols defined for the data link layer to deal with flow and error control. We can divide it into 2, one for noiseless channel, the other for a noisy channel. For the noiseless channel, we have simplest and stop wait. For the noisy channel, we have stop and wait ARQ go back and ARQ, and selective repeat ARQ. Although the first three protocols are still used at the data link layer, the last two have disappeared. Note that the samples are focused on unidirectional transfer. There are specialized frames like the ACK or acknowledgement and NACK for negative acknowledgement. In piggybacking, NACKs and ACKs are included in the data frame. All of these protocols are implemented in software. Our first protocol is the simplest protocol, with neither flow nor error control. We assume that the receiver can immediately handle any frame it receives. In other words, the receiver can never be overwhelmed with the incoming frames. Our next protocol is the stop and wait protocol, which uses both flow and error control. If the data frames arrive at the receiver site faster than they can be processed, the frames must be stored until their use. In this protocol, the sender sends one frame at a time and waits for an acknowledgement before sending the next one. To detect corrupted frames, we need to add a CRC to each data frame. When a frame arrives at the receiver site, it is checked. If its CRC is incorrect, the frame is corrupted and silently discarded. The silence of the receiver is a signal for the sender that the frame was either corrupted or lost. The stop and wait ARQ protocol is a connection-oriented protocol that provides flow and error control. Redundancy bits are added to the data frame. At the receiver end, if a frame is corrupted, it is silently discarded. Numbering frames allow detection of lost frames. Corrupted and lost frames must be resent. The sender maintains a copy of the sent frame and starts a timer. If the timer expires and no acknowledgement is received, resend the frame. Acknowledgement frames can also be corrupted. To prevent duplicate packets, the protocol uses sequence numbers and acknowledgement numbers. A field is added to the packet header to hold the sequence number of that packet. In sequence numbers, the smallest range that provides unambiguous communication is selected. This is also to minimize frame size. If m bits long, the sequence numbers start from 0 to 2 raised to the m minus 1 and then are repeated. Acknowledgement numbers announces the next sequence number expected. Stop and wait ARQ, the sequence number and acknowledgement number are based on modulo 2 arithmetic. Here is how stop and wait ARQ works. Take note of how the sequence numbers and acknowledgement numbers change their values. At the start, the timer starts. Here, the first frame is sent with the sequence number of 0. It will arrive at the receiver end. The receiver will send an acknowledgement number of 1. The next frame, the sequence number will be 1. However, this frame got lost. After some time, the timer will expire. Since the sender did not receive any acknowledgement, the sender will resend the frame. The receiver will receive the frame, then send an acknowledgement number of 0. Here is another scenario. The timer will start. Frame 0 will be sent. The receiver acknowledge it by sending acknowledgement 1. However, acknowledgement number got lost. After some time, the timer on the sender side will expire. The sender will resend frame 0. At the receiver end, it will see that it's just a duplicate. It will discard duplicate, but it will still send acknowledgement 1. The The stop and wait protocol is very inefficient if our channel is thick and long. By thick, we mean that our channel has a large bandwidth or high data rate. By long, we mean the round trip delay is long. The product of these two is called the bandwidth delay product. We can think of the channel as a pipe. The bandwidth delay product then is the volume of the pipe in bits. The pipe is always there. It is not efficient if it is not used. Bandwidth delay product is a measure of the number of bits a sender can transmit through the system while waiting for an acknowledgement. In networking and in other areas, a task is often begun before the previous task has ended. This is known as pipelining. There is no pipelining in the stop and wait protocol because a sender must wait for a packet to reach the destination and be acknowledged before the next packet can be sent. Pipelining improves the efficiency of the transmission if the number of bits in transition is large with respect to the bandwidth delay product. To improve the efficiency of transmission, multiple packets must be in transition while the sender is waiting for acknowledgement. In other words, we need to let more than one packet be outstanding to keep the channel busy while the sender is waiting for acknowledgement. Here, we will discuss go back N. The key to go back N is that we can send several packets before receiving acknowledgements, but the receiver can only buffer one packet. We keep a copy of the sent packets until the acknowledgement arrive. Here, sequence numbers are modulo 2 raised to the m, where m is the size of the sequence number filled in bits. Acknowledgements or acks are cumulative. More than one frame can be acknowledged by a single acknowledgement. Here we introduce some new concepts. First, the sliding window. It is an abstract concept that defines the range of sequence numbers that is the concern of the sender and the receiver. The send sliding window is an imaginary box covering the sequence numbers of the data frames which can be in transit. It can slide one or more slots when a valid acknowledgement arrives. The receive sliding window is an imaginary box of size 1. The window slides when a correct frame has arrived, sliding one slot at a time. Here is a send window for go back N. Here, m is equal to 4. The send window size is 15. The orange part are the outstanding frames. Those frames are sent but have not been acknowledged. The clear part are the next frames that can be sent while waiting for the acknowledgement. Here is a receive window for go back N. As you can see, it has only one slot. The left sides are the frames already received and acknowledged, while the right side are the frames that cannot be received until the window slides. In go back N, only one timer is used since the first outstanding frame always expires first. The silence of the receiver causes the timer of the unacknowledged frame at the sender side to expire. Sender resends all outstanding frames. For example, the sender has already sent frame 6, but the timer for frame 3 expires. The sender must resend frames 3, 4, 5, and 6. This is why it is called go back N. Here is an example of the go back N with a reliable forward channel. The send slide window size in this case is 7. The first frame is sent with a sequence number of 0. This will be marked as an outstanding frame. At the receiver side, since it is the expected frame, the receiver slide window moves to the right. Then it sends an acknowledgement number of 1. The sender will receive the acknowledgement number and will unmark and move the send slide window to the right. Next, frame 1 will be sent by the sender and will be received by the receiver. However, the acknowledgement number is lost while being sent. At this point, the sender continues sending frames 2 and 3. The receiver keeps receiving it and moving the receive slide window to the right and sending acknowledgements. At this point, Act 3 is received by the sender, so all the outstanding frame before it will be unmarked and move the send slide window to the right. Here is another example of go back N where there are lost frames. Frame 0 is sent, received, and acknowledged without issues. However, frame 1 is lost. The sender keeps sending frames 2 and 3. However, the receiver is still expecting frame 1. When frame 2 and frame 3 arrives at the receiver side, no action is taken. The timer for frame 1 will expire and it will resend all outstanding frames. Stop and wait ARQ is a special case of go back N ARQ with a send window size of 1. The go back N protocol simplifies the process at the receiver. The receiver keeps track of only one variable, and there is no need to buffer out-of-order packets. They are simply discarded. However, this protocol is inefficient if the underlying network protocol loses a lot of packets. Each time a single packet is lost or corrupted, the sender resends all outstanding packets, even though some of these packets may have been received safe and sound, but out of order. If the network layer is losing many packets because of congestions in the network, the resending of all of these outstanding packets makes the congestion worse, and eventually more packets are lost. This has an avalanche effect that may result in the total collapse of the network. The selective repeat ARQ, which as the name implies, resends only selective packets, those that are actually lost. It is more efficient for noisy links. However, processing at the receiver is more complex. The send window max size is 2 raised to the m-1, which is the same size in the receive window. It is smaller than the go back n. It is less efficient, but fewer duplicate frames. As mentioned, the selective repeat protocol also uses two windows, a send window and a receive window. However, it is different from the go back n. First, the maximum size of the send window is much smaller. It is 2 raised to the m-1. Second, the receive window is the same size as the second window. The selective repeat protocol allows as many packets as the size of the receive window to arrive out of order and be kept until there is a set of consecutive packets to be delivered to the application layer. Because the sizes of the send window and receive window are the same, all the packets in the send packet can arrive out of order and be stored until they can be delivered. We need, however, to emphasize that in a reliable protocol, the receiver never delivers packets out of order to the application layer. Here's an example of the selective repeat ARQ. At the sender, frame 0 is transmitted and acknowledged. Frame 1 is lost. Frames 2 and 3 arrive out of order and are acknowledged. When the timer times out, frame 1 is resent and is acknowledged. The send window then slides. At the receiver side, we need to distinguish between the acceptance of a frame and its delivery to the application layer. At the second arrival, frame 2 arrives and is stored and is marked, but it cannot be delivered because frame 1 is missing. At the next arrival, frame 3 arrives and is marked and stored, but still, none of the frames can be delivered. Only at the last arrival, when finally a copy of frame 1 arrives, can frames 1, 2, and 3 be delivered to the application layer. The protocols we discuss are all unidirectional. Data packets flow in only one direction, and acknowledgements travel in the other direction. In real life, data packets are normally flowing in both directions, from client to server and from server to client. This means that the acknowledgements also need to flow in both directions. A technique called piggybacking is used to improve the efficiency of the bidirectional protocols. When a packet is carrying data from A to B, it can also carry acknowledgement feedback about arrived packets from B. When a packet is carrying data from B to A, it can also carry acknowledgement feedback about the arrived packets from A. The figure shows piggybacking in go back N ARQ. This ends Module 13. Thank you.